Okay, hey everybody. So here we have a friction problem, and our problem says that I have a diagram that shows a 4 kilogram object accelerating at 10 meters per second squared on a rough horizontal surface. And then I see a force diagram with an applied force of 50 newtons to the right and a frictional force to the left. And even though the diagram is not drawn to scale, there is a noticeable difference in the size of the arrows. And so the rightward arrow, the 50 Newton applied force or pulling force arrow, is noticeably larger than the leftward friction arrow. And then I'm shown again that I have an acceleration, and not only its magnitude twice, I'm shown that in the problem and then on the diagram, but then they also tell me that the acceleration is to the right. And so the first thing I want to address is this sequence of words right here, 4 kilogram object. And one of the things we've talked about is that when they use that type of sequence, a 4 kilogram object, or for instance, another example might be a 5 Newton object. And so in this particular case, 4 kilogram object, what they're telling us is the mass of the object. And the unit kilogram should tell us that it's a mass. And which mass are they talking about? They're talking about the mass of the object. And so let me list that given. I have a 4 kilogram mass. And then I have an acceleration of 10 meters per second squared. And if I have an acceleration, I should automatically realize that I do not have a balanced forces situation, that I do have a net force here. Net forces cause accelerations, and so the friction force is either larger or smaller than the 50 Newton rightward force. And actually, because of the direction of the acceleration, I should already know that it's smaller, because the acceleration will always be in the same direction as the net force. The net force, therefore, is to the right, which means that this must be smaller than this. If I have a net force to the right, that means that the left force is smaller than the right force. And so right now, these are the only givens that I have. And so I am looking for the force of friction. I'm sorry, and I have one other given. And I have the applied force, or what I'm just going to call quite simply the pull. And so I have a pull of 50 newtons. And in past problems, and it would be understandable if you did this here, if when asked to solve for the force of friction, the most obvious thing to do is look to the reference table and see that there's a formula that has FF in it, and that formula is that the force of friction is equal to the normal force times mu times the coefficient of friction. And because this object is moving, it would be the coefficient of kinetic friction. And it would be very understandable to be tempted to try to force that formula into this problem. Unfortunately, this formula is unusable for this problem. So there must be another way to solve for friction. Now let's talk about some of the clues in the problem that I shouldn't try to use this formula. And the biggest thing is that while they do call the surface that the object is on a rough surface, and really the reason they do that is because so many problems in Regents physics involve frictionless environments. And so they're trying to get you to realize that this is not one of those scenarios. Obviously, the fact that they ask you for friction and they put friction on the free body diagram, and this diagram is taken right from the problem itself, so this was included with the problem, should be a clue that there is friction in this problem, that it's not a frictionless environment, but they're just emphasizing it. That's how they're using the word rough. But what they don't tell you are the materials of construction of either the box or the floor, the surface that it's on. They don't tell you it's a wood box on a wood floor or a steel box on a steel floor. When you don't have the materials of construction, when you don't know what the surfaces are made of, there is no way that you will ever use this formula. Because without those surfaces, you have no way of finding this. Now, the only exception to that is if they ask you to solve for the coefficient. So the only time you will ever use this formula in the absence of being told the surfaces is if they're asking you to solve for the coefficient. And so, once again, I'm being asked to solve for friction, and the problem doesn't tell me the surfaces. So this formula is out. This isn't even a two-step solution where I ultimately use this formula. I will never be able to use this formula to solve for friction if I don't know the surfaces. And so here we have a second way to solve for friction, and that involves finding the net force and then writing a sum of the forces equation. And so I'm given an acceleration and I'm given a mass. And if I know those two things, I can calculate the net force on the object. Now, remember, there are two individual forces acting on the object. The combination of these forces, the vector combination, is what gives you the net force. But right now, I calculate the net force, or I'm going to calculate the net force, using this formula. So it's kind of a reverse engineering problem. And so when I do my plug-in, I get 10 equals F net over 4. And so when I rearrange, F net equals 10 times 4. F net equals 40 newtons. Okay, so that's my overall force. Well, what would the sum of the forces equation look like? It would look like this. The sum of the forces in the x. Now remember, sum of the forces is the same thing as F net. These are two ways of saying the same thing. And obviously, the net force in this problem is in the x-axis. Are there individual forces in the y-axis? Of course. The weight is down, the normal force is up, because this object is on a surface. But the reason we don't include them is because they really don't factor into this problem. All of the action here is taking place horizontally. I don't need the normal force because I'm not using this formula. And so the sum of the forces in the x, well, what are the two individual forces I have? I have a pulling force, and since I know the value for that, why would I even list it symbolically first? I know that it's equal to 50 minus FF, which is what I'm solving for. And while I don't know this guy yet, I know that this minus this equals 40. Because I know that the sum of, I already found out the sum of the forces. The sum of the forces is F net, 40 newtons. And so obviously, the only number that can go in here to make this equation work is that the force of friction is equal to 10 newtons to the left. Now, saying left is kind of a little unnecessary here, because I have a diagram that showed me very concretely that the force of friction was to the left. And so the last thing we want to talk about is that we have now come to basically the conclusion of learning about friction. And one thing, or what we have learned, is that there are three ways that we can solve for friction, or that we are expected to be able to solve for friction. And the first way is this. We are expected to know that friction is equal and opposite to the applied force if I have a constant velocity scenario. So that's one way. You're not using an equation, you're just using your logic, but that is a friction question. And so, for instance, on page 56 in the Regents workbook, question number 127, the information that I am given is as follows. A horizontal force is used to pull a 5-kilogram cart at constant speed. And if I see the words constant speed, or another way of saying constant speed is zero acceleration. If I see those words, then I know that friction is equal and opposite to the applied force, which means if I'm told the applied force, I automatically know the friction force. If I'm told the friction force, I automatically know the applied force, the pulling force. The second way, which is what we did in the previous video lesson, is to solve for friction using the formula that friction equals the normal force times the coefficient of friction. So what are the clues that you're going to use this approach? Well, look at this problem. A force of 10 newtons toward the right is exerted on a wooden crate. initially moving to the right on a horizontal wooden floor. The clue that you're going to use this approach to solve for friction is if you're told the materials of construction. I have really never seen a problem where you're told the materials where you don't use this formula. And so now we have two ways to solve for friction. If we're told constant speed, almost always friction is going to be found by applying the logic that it will be equal and opposite to the pulling or pushing force, the applied force. And if we're told the materials of construction, almost always we're going to use this formula. Now, are there other little details? Sure. We have to realize that the normal force is equal and opposite to the weight. So maybe they would throw us a little curveball in here and tell us, rather than telling us the weight directly, and they're never going to tell us the normal force directly, they would tell us the mass. Well, in that case, if I'm using this approach, before I even go to this formula, I would have to use the mass to find the weight using this formula. So just realize that there are some other little wrinkles, but these are the general approaches. And so what's the last approach that we just covered in this video? It's using the fact that I can't use this formula to solve for friction if I don't know the surfaces. And so in these problems, I'll be given typically the acceleration and either the mass of the object, or sometimes, if it's a little harder, the weight of the object. Remember, in this formula, this is a constant. G is the acceleration due to gravity on Earth, negative 9.81 meters per second squared. So if I'm told the mass, I can easily find the weight. If I'm told the weight, I can easily find the mass. In this formula, I would need to know the mass, and sometimes they make me work for it. And so, if I'm not told the materials, but I am told the acceleration and either the mass directly or a way to find the mass, meaning they tell me the weight, then I first solve for F net using this formula and then write a sum of the forces equation like I did in the previous problem. And so, for instance, in this problem, the key that would clue me in that I can't use this is that even though they tell me it's a rough horizontal surface, they don't tell me exactly what surfaces are involved. And so that means I have no way of knowing the coefficient and using that table on the reference table.